think it's about time to kick off then. So welcome back to all of those who attended this morning's webinar about the mechanical projects from the Powertrains Research Hub. I think it was a really interesting session, and if anyone missed it, it should be available from Offshore Renewable Energy Catapult's YouTube channel, so you can head there to catch up. Now, those who are new to this afternoon session, welcome. My name is Dr. Di Lewis, and I'm the Senior Academic Engagement Manager for the Offshore Renewable Energy Catapult. I manage ORE Catapult's Academic Engagement Programme, and within that sits the Research Hubs. And for the last couple of years, I've also been managing the Powertrains Research Hub from the Catapult end. Today, we'll be presenting projects that have been undertaken within the PTRH, with the afternoon session covering the electrical engineering projects. So a little overview of the agenda. We will initially have an introduction to ORE Catapult from myself, followed by introductions from the programme technical leads from the Catapult, and then from the universities of Sheffield and Warwick, followed by the technical presentations. In some cases, we'll have the students presenting their own work, and in others where the project is finished or the student is unavailable, the supervisor will give an overview on their behalf. I hope we should have time at the end as well for a Q&A session, so please can you put any questions you have in the Q&A box as we go along, and if we don't have any time to cover everything, we can follow up after the session. We aim to close then by 2:30, so you can all get back to your days then. So initially, a brief intro to ORE Catapult. Our vision is to enable innovation and accelerate the development of offshore renewable energy, growing businesses and creating jobs throughout the UK. We have world-class facilities, researchers and engineering capabilities, and it is our aim to reduce the cost and risk in the renewable sector in order to grow the industry in the UK. We are part of the Catapult network. The Catapults were established by the UK government in areas of strategic importance to the UK economy, with the aim to develop capabilities to become world-leading in these particular sectors. Catapult Network supports businesses in transforming great ideas into valuable products and services, delivering impact across the UK economy and enabling businesses to thrive in global markets. There are 9 catapults in total, including Energy Systems, the Digital Catapult, and High Value Manufacturing, along with ourselves. We are now at approximately 230 employees, following rapid growth as we support the broad UK renewable sector and its kind of evolving challenges. We have offices throughout the UK in Aberdeen to support the transition from oil and gas, Blyth, where we have our large-scale testing facilities, Fife, Glasgow, Hale, the Humber, which is a very important O&M base, Lowestoft, and Pembroke Dock. As can be seen, we also have a number of bases established within a number of universities through our Research Hub programme. The Research Hubs are part of our larger academic engagement programme, which was set up in areas of strategic importance to support the development of the wind industry in the UK. The overall aims of the Research Hubs are cost reduction in CapEx and OpEx, increased energy yield, and reduced environmental impact. The Windblade Research Hub, with the University of Bristol, focuses on the development of more efficient and sustainable wind turbine blades. The Electrical Infrastructure Research Hub, with the Universities of Strathclyde and Manchester, focused on developing electrical infrastructure required to support the transition to renewables. And the Powertrains Research Hub, with Universities of Sheffield and Warwick, focused on the development of larger, more efficient wind turbine powertrains. There were a number of motivations for us in developing the Powertrains Research Hub, all based around essentially improving the reliability and affordability of wind turbine powertrains as they get larger and larger, in order so we can meet our 2030 and 2050 net zero targets. We worked with a range of stakeholders and aimed to disseminate the research to as broad an audience as possible across industry and academia. And since its inception, we've developed a strong collaboration with the Universities of Sheffield, Warwick, Strathclyde, and Northumbria, and have also undertaken a research programme with GE through the Research Hub. We've undertaken a large number of co-funded PhDs and research projects, and disseminated the work at many international conferences and a broad range of journal articles. So I'll now hand over to our to Chenjiang Jia, who's our head of powertrain conversion, to speak about essentially how the work from the PTRH has supported us at Ori Catapult.
Thank you, Dai. I'm Chenjiang Jia, and you can call me CJ. I'm a head of the power conversion. So can we go to the next slide? So this Ori Catapult Powertrain Research Hub established 2019. It's between ourselves and the University of Sheffield and the University of Warwick. The main objective is are designed to improve the reliability and develop a advanced test methodologies for offshore renewable energy. The second point is to develop advanced health condition monitoring and prognostic technologies using AI or machine learning. The last point is to develop the next generation powertrain components, especially for the large sized wind turbines and the floating offshore wind. Should we go to the next, please? So far, it's already 5 years, and we developed a series of electrical research projects. This included sponsored PhDs and also research associate. So accordingly, there are three categories: reliability and condition monitoring part, and next gen turbine side. So you will see in the first column from your left-hand side, the reliability point of view, we have this feasibility modeling and design a short-term overloading capability of power module. So mainly for HVDC grid support. So I think this is with Warwick University. Later, Nicholas will give more detail on that topics. And then we will with effect of high humidity on power module. This is with Antonio with Sheffield University. Later, more detail will be present. The last part in our reliability part is the common mode voltage reduction for motor drives. This is also with Sheffield. So in the middle bit, you will see this condition monitoring part. The project 13 is about fault modeling and diagnose of multi-phases PM machines for offshore wind application. This is with Sheffield. And then the 17 electric project is a development of digital twin for virtual validation for the power converter. This is with Yang Hao from Warwick. So today he will also give the presentation later on. So this one, I think is measurement and characterization of bipolar degradation of silicon MOSFETs. This is labeled with XX. I think still either under discussion or we need to find out the right number for this. The next gen turbine in the last column. So in this case, we have the silicon MOSFET in offshore turbine converter system, and also power on fiber for offshore multiple modular converter for HVDC applications, and also customized capacitor design for MMC HVDC with more reduced size and weight. The last part is about the recyclable IGBT power module for offshore wind turbines. Those at the last column, you will see some pictures and the images. These are according with this relevant projects. I think that's the kind of overview of the whole projects. That's all from my side.
Hello, folks. Dave Stone. I'm the technical lead of the Powertrain Research Hub in Sheffield. Over the last 5 years, it's been really useful for us to work with Oric and with Warwick on various aspects of the powertrain, from the electronics through to the machine design. Hopefully you will enjoy the hearing some of the details of some of the interesting projects from our members moving on. But I just wanted to say welcome and hope you enjoy the rest of it. So thank you very much.
Hi, good afternoon. And my name is Li Yuan from Warwick University. Next slide, please. I'm the academic lead at Warwick, and it was very fortunate for me to work with my colleagues and the students in the last few years in this hub. And we also, Warwick University has a close collaboration with Chongqing University in China. We have a joint laboratory in silicon carbide power electronics. Therefore, some of the projects were conducted in collaboration with Chongqing. So, as CJ mentioned, that we have selected two projects to be presented today in more details. That's E9 and E17. And there are 5 more projects which we don't have opportunity to present today, but I'm going to outline very briefly what they are about, and then if in the future anybody would be interested in any of them, we would be very happy to please contact the cardport, and we would be very happy to expand the discussion. Next, please. Right. The first one is about silicon carbide MOSFETs for offshore wind turbine converter systems, particularly for the grid-side inverter. And we developed a multi-objective optimization method for design. We also designed included the design of the grid side filter, and as well as the cooling system, to bring out the characteristics of silicon carbide devices. At the end of the project, we developed a 30 kilowatt and high power density prototype inverter, and to verify the models. And next, please. This project was on bipolar degradation of silicon carbide MOSFETs, and the intention was to understand the degradation, the nature, and as a result, this is to support how to use the body diode in the MOSFET so that the converter can be more compact. Also we discovered that the nature of the degradation develops very quickly, therefore, and the problem became actually a device selection screening, or the degraded, and most of the degraded devices could be used under a derating condition. Next, please. Right. This was an adventurous project about capacitors in the MMSC system and MMC submodule, and the capacitors occupy at least 50% of the volume and maybe more than 50% of the weight. And in offshore conditions, the size and the weight are both very important factors, so we want to reduce them. And the idea was to explore, to optimize the capacitor dielectric material so that under the MMC converter conditions, the properties of the capacitors in multiple dimensions are utilized as towards the limits almost simultaneously. Our initial study to modify the dielectric material showed that we could easily achieve about 18.7% size reduction. Further optimization would bring out more benefits. And final one, I think. Next is a final one, which would be the final one is some sort of details. This is about again reliability for MMC high voltage systems in general. As we know, IGBTs cannot be triggered like thyristors, and we have to maintain the gate drive signals, and it would be quite difficult to provide power supply in a high voltage condition because the insulation cost could be very high, and the electromagnetic noise could be a problem, could be difficult or expensive to handle. Therefore, we came up an idea to provide the power supply to the gate drivers by power on fiber, using optical fiber. And that's about this project. The final one, we are still in a very early stage of study. Next slide, please. This is about recyclability of power modules in the future. And our idea is to try to avoid the materials or components which are not recyclable or difficult to recycle in the power module, so that the power module can be more easily recycled with low cost. Therefore, this study is still in a very early stage, and we hope to have the opportunity to share the findings in the future. Thank you very much.
Okay, hello everybody. So my name is Miliana, so I'm a academic supervisor in this particular project on MMC. Yeah, next slide, please. Okay, so the title of the project is Optimization of a Modular Multi-Level Converter for Medium Voltage Wind Energy System. So my presentation today will cover briefly MMC introduction for wind energy, and then I will talk about our main research activities, findings conducted so far, and then a suggested next step in this project, because this project is continuous into the next year as well. Thank you. Next.
Emiliana, your camera isn't working properly. No,
well, I can. It does work, so I can see myself. So I don't know if
no
others.
We'll.
All right. Yeah. Okay, so here is the brief introduction. So from the left top side is a classical two-level power converter. So it's widely used for power levels up to 8 megawatt. This is usually typically for grid connection, low voltage, 690 volt. So the difficulties here is scaling to higher power levels. And so from the right side is our proposed solution. So go for a modular multi-level converter, so modular MMC. And, MMC in general is kind of easy to scale up for higher voltages and powers. So if you can see, each leg has a cascaded connection of submodules, here noted like a SM submodule. And so we looked different submodules, and they are forming like an upper arm, lower arm, and yeah. And so we'll talk about that later on. So when it comes to different submodules topologies, so we look, it could be different topologies, but we looked at the traditional one, which is one leg, a hull bridge, which is just below this MMC figure. And then in the middle is the solution. If you can maybe just one click, there is a one animation. If it just highlights, if it works, right? Yeah, so this is the full bridge MMC. So this is the maybe solution that we find the best for the wind. And then also the next topology would be hybrid topology, where we are using some modules are hull bridges, some modules are full bridges. So each sub-module has that capacitor, flying capacitor, and that flying capacitor basically is the problem, because in MMC it sees the fundamental frequency. So from the wind side, generator side, it can see as low frequency as 5 Hertz. And then the size defines, that frequency defines the size of capacitor. So our main research question then is formed by that difficulties in MMC. So we are trying to overcome that. Okay, next slide. Okay, so here is the first, maybe just one, also 2 clicks. Yeah, so there are some animations. Yeah, one more. Yeah. And so it is so we are talking here about full bridge MMC. And for the full bridge MMC, what we recognize that we can optimize energy storage requirement by actually optimizing input-output voltage ratio. So full bridge MMC allows us that we can independently control DC and AC voltages, input-output voltage. And by then finding optimum ratio, we can actually minimize the energy storage requirement. So here, what we are looking in the, like a parameters, which is optimizing here on the on the left top figure in color. So showing the total energy stored per watt ampere. And so that kind of total energy constant here is not dependent on the number of submodules that we put in each arm, which is the nice parameter for optimization. So that is shown in that figure, top left on a y-axis is this parameter Km. So that is that ratio between the output voltage and input voltage, which is basically also what we call boost ratio. And then on x-axis is the power factor. So we can't optimize that. That is given by application. And so what we can then play with is this Km parameter, right? What we are optimizing. And those yellow part in this figure are basically showing us where the minimum energy requirement is. And in the middle figure shows that energy, total energy constant, Hn, kind of for different power factors. So if you can click just once. So this would be that curve, which shows that energy constant for the active power only, when the unity power for unity power factor. And we can see here minimum energy required for particular ratio between output and input voltage, which would corresponding to 1.4, which would be 60% reduction of DC link voltage with respect to the nominal classical solution. And then the most right figure shows again this optimization of energy, but then we are considering maybe a range of the power factors, not just one power factor. So that's kind of plus minus 40, 90. So can you just click once more? Yes, so this is showing now different optimum if we consider the range plus minus 90 degrees power factor. And for this particular case of this range, so we talk about like a reduction in energy storage requirement about 35%, so which basically relates directly to the size of capacitance, right? So it's all about kind of connected. So it's a kind of significant. So what we in our first approach to increase power density of MMC, so our first approach here is basically to find that kind of optimum voltage level, and basically which leads that we reduce the size of each submodule. Okay, thank you. So next one. Yeah, so this is, yeah, so just one more click. Yeah, I forgot about this. Yeah, one more click. Yeah, so this would be just when I talk about reduction. So this would be that reduction with respect to conventional. This would be conventional Km is 1. And then kind of we kind of propose work in a boost ratio. Okay, so next slide. So here is this is the second step in our optimization approach. So first was how we can reduce the capacitance, and then now is how we can increase output voltage levels. So we would like for the minimum number of the cells, submodules that we use, get as much output levels as possible, as that would actually increase power quality, so we can get rid of the filter. And the approach that we take is here what it says, phase shift interleaving. So we talk about interleaving angle between the upper arm and lower arm voltages. So if you can click 2 times. Yeah, so these are some waveforms of cell. So if you start from the left top side, so it would be submodule voltage, arm voltage, upper arm voltage, and then output voltage. So we can see 2 figures for output voltage. So if you maybe click once. Yeah, so here highlighting especially this blue part, highlighting output voltage. So we can see visually that one output voltage waveform has more levels than the right one. So one is having 15 levels, another is 8 levels. So we found analytically, basically by harmonic elimination, so we found the optimum phase shift for specific output voltage ratio. So that changes with different output voltage, input output voltage ratios, but for the optimum one, so that would be the angles. They depend on the number of submodules, positive, negative, and other details. If you just click once more and once more. Yes, so this would be then also some kind of indication how we can calculate number of output voltage levels for a given number of submodules. And also what is important here, output voltage effective switching frequency is quite pushed away from the fundamentals. So basically in our designs, we actually didn't have any need to have output voltage filter. So this is these 2 steps of our optimization approach, how we can squeeze in and increase the size of the MMC. Okay, so next slide. So the next part will be just showing some comparative analysis that we conducted for the optimized designs of MMC, and we did it with respect to the 2-level converter, which is kind of widely available that we can find some information about. So in this optimized analysis, we considered the grid power, voltage requirements, so power control mode, reactive current mode, wind turbine characteristics, so considering wind speed, the probability curve. Yeah, okay, next slide. So here it's a kind of design flow. So how we actually optimize further, I mean, in order to be able to compare the different MMC designs. So we use the IGBT modules, which is more optimum for 2-level converter. But that was kind of for us a starting point, and we just wanted then to use the same module and play around with different topologies, see if we can actually get better solution using the same power devices. Again, those power devices are not really optimum for MMC. So 2-level converter, so we with the system, so we only looked like a low voltage 690 volt grid. For the MMC, we looked medium voltage grid, so 6.6 kilovolt. What we did, we tried to kind of push as much current through those devices as possible for a given topology, and just kind of looking at the hottest device when it reaches maximum junction temperature of 100, that was kind of for us indication that's the kind of maximum it can reach. Yeah. So next one. Okay, so this is just a zoom in one of the designs. So this is full bridge. And so we managed to kind of using those devices, basically to squeeze in a power of 18.7 megawatt amp. So that is the rated power using just one unit. So we don't need to parallel like we normally do with the classical two-level solution. Okay, so these are some details, so we can go next. Okay, so this is maybe interesting because our target was basically when we did optimization to look at the volume and weight of those required capacitance for our MMC. So what we looked here, and this table is showing comparative analysis between starting with the classical MMC, which is shown in red, so the top row, and then some optimized improved models, and then finally we come to those which is highlighted in green. So this is full bridge MMC optimized with some also injecting a circulating current approach to further improve reduce the energy storage requirement. And so we actually managed to kind of significantly reduce the size of required capacitance by 75+%. So quite significant improvement in the reduction in the size. Okay, so I can maybe just, I can mention here. So when we looked capacitance, so we needed to go for the film capacitor, rather than electrolytic capacitor, as the RMS current requirement ripple current for MMC is kind of we couldn't find, or it would be too big size when it comes to electrolysis, so it would need lots of those in parallel to be able to cope with the RMS capacitor current ripple. So film capacitor, so what is here is showing different designs starting from the left of the Hall bridge. Then if you can click maybe once more. Yeah, so here is the kind of optimum solution for the full bridge. So what we are looking here is the cost of the IGBT and capacitors. So this blackish area is the capacitors, and IGBT is those white with the dotted signs. So we can see from the left side that Hall bridge needs lots of capacitance, so cost is high, and we can see this optimum solution, so we're squeezing capacitance, and so then cost as well. But we can notice that then IGBT we need more because it's a full bridge, so we have more devices. Then we said, okay, we can maybe combine, go with the hybrid solution. So if you click once more, so that would kind of be last, or at least, you know, at the moment what we have when it comes hybrid solution. So trying to not to reduce the capacitance, but then maybe reduce a little bit need for the IGBTs. Yeah. So increased converter cost of MMC definitely will be increased with respect to the two level because of the cost of capacitance. At least, I mean, you know, this cost shouldn't be taken like an absolute value because it's not customized capacitors that we use, and also it's not for the mass production. So, you know, it was really quite basic. So it's more like comparative rather than the absolute values. But what we say, even if they pay more initially for capital cost, then because of efficiency, if you go for the next slide, so that's kind of, yeah, next slide, yeah. So here is the efficiency. If you can maybe click once. This is the IGBT that we are mentioning before. So these are efficiency curves with respect to the power of different designs. So if you click once, so this would be for two-level converters. So we can see quite low efficiency, especially for the low powers, switching losses. And then if you click once more, so this would be solution of efficiency for the full bridge. So we have more devices, yeah. So, but efficiency is significantly improved with respect to the two-level. And then the next click. So here is the hybrid. So we reduce number of IGBT, so we can actually improve further efficiency. So as I said, here is not the optimum selection of devices for MMC. It's more optimum for two-level, but we just wanted to see if we can actually improve efficiency. And so those numbers of efficiency, we believe we can be boosted much more. So this is just an initial study. Yeah, so that's the next one. So here, just in green, maybe highlighting, significant reduction in the capacitance that we managed to achieve through two steps optimization process. From one side, optimum ratio output input voltage, from other side, that optimum phase shift interleaving between the upper and lower arm voltages. Okay, so the next slide, maybe this is the last slide. So here is the covering the next steps. So next steps, so till now we came up with the new modulation strategy for the hybrid. We are presenting that at the next ECC Europe in Germany, and then also control balancing strategy. Hybrid is quite challenging for controlling, so here we came with some new strategies. So we're preparing journal publication. So our current research directions goes in two ways. From one side, we would like to optimize actually sub-module with respect to devices. So we have some ideas of hybrid silicon carbide devices to use in either hybrid MMC and full bridge MMC, but together with the kind of optimized modulation strategy. And from other side, there is some solution which already developed by ORECT when it comes how to control MSC by not having the same average voltages of all sub-modules, but rather kind of unequal, and that optimum unequal capacitor voltage levels might actually boost even further the number of output voltage levels. And these are kind of two maybe streams that we would like to work on further to optimize the MMC for wind. Thank you. Yeah, so that's basically close the presentation.
Good afternoon. I'm Antonio Griffo from the University of Sheffield. I'm presenting the research carried out by my student, Mark Sheriff. Next, please. Yes. So this project deals with the reliability of offshore wind power converters, in particular understanding the influence of operation of power electronics and power modules in particular in the offshore wind environment. So power electronics is considered to be one of the largest contributors to wind turbine failure. This is mostly due to the harsh environment at which they are subjected, due to large variation in several stressors like temperature, humidity, contamination, and so on. So while the effects of temperature and temperature cycling is on power electronics reliability is well understood in literature, the effects of humidity and moisture on the short-term and long-term performance is not entirely clear. This provides the motivation for this research, specifically understanding the short-term effect of moisture ingress through the silicon gel that passivates most power modules, as shown in the pictures to the right. it's been known in the literature that moisture, once it penetrates in the power module substrates, can cause long-term corrosions and dendritic growth in the DBC copper substrates that are used in power modules. But what are the effects in the short term, both on the reliability aspect and on the performance aspect on the power modules? So this provides the motivation of the project. Next, please. So the three main research goals were identified in this research. The first was to understand how the properties of the encapsulant, which typically is a silicon gel, which is a polymer obtained by the polymerization of silicon vinyl and silicon hydride into long chains into a long chain structure, how this material is influenced by high temperature and high humidity, and by combination of these two stress factors. Do these changes in the properties, on the dielectric properties of silicon gel, have an effect on the variation of IGBT's switching characteristics, both in the short term and in the long term? And is there an effect on reliability, in particular on partial discharge and partial discharge inception voltage in power modules due to the absorption of humidity into the silicon gel? Silicon gel, as I said, is a polymeric chain, but when it's cured, it might contain imperfections, it might contain voids, and can trap moisture and other contaminants. And therefore, yeah, we were interested in understanding how this affects the reliability and how it interacts with the standard substrate used in power electronics converters. Next, please. To answer the first question, so how the electrical properties of silicon gel, in particular the dielectric constant, how it's affected by penetration and absorption of humidity. We have developed a series of test systems using custom designed interdigitated capacitors that have been placed under cured silicon gel in various with various layout and various environmental conditions. So to summarize, tests were conducted to understand the effect of humidity only, temperature only, and the combination of both for various duration of test cycles, various types of cycles, and also various thickness of the gel samples, as well as various orientation of the samples themselves. Next, please. In summary, some of the results are presented in this slide. On the left column, there are a number of results that shows the effect on dielectric constant, both real and imaginary part, for various temperature-only steps. This shows a relatively minor effects of temperature on the dielectric properties of the material. The column in the middle shows the effect of humidity, variation of relative humidity while keeping temperature constant. In this case, the effect is quite significant, with up to 10 to 15% change in the real part, and over 200% change in the imaginary part of the dielectric constant. But when both temperature and humidity are combined, this is where the effect is most dramatic. In here, in particular, on the right-hand column, you can see that there are changes of up to 100% in the value of the equivalent capacitance of the dielectric gel, and these suggest that there might be short-term effects on the electrical properties of the silicon gel. Another interesting aspect was the understanding the effect of different thicknesses of gel, and as expected, of course, the higher the thicker the passivation substrate, the slower the effect on the diffusion of the humidity in the substrate. Next, please. So in conclusion, for this aspect of the work, temperature alone showed only minor changes in gel dielectric properties, but the largest changes were observed when both combined and temperature and humidity were applied, resulting in a significant variation of the parameters. Another interesting aspect is that some of these changes might be due to condensation and pooling of humidity when the devices are placed in a horizontal orientation. So that's where the test on the right shows that by placing the devices upside down, basically in this inverted orientation, the diffusion penetration of humidity into the substrate can be significantly slowed down. Next, please. Due to this variation of capacitance, equivalent capacitance of the silicon gel, we were interested in understanding what could be the implication in terms of switching characteristics into the power devices. That's where this test setup, which represents a standard double pulse test, were conducted on a series of devices typically used in the wind converters. Next, please. So we conducted a series of tests on a number of devices in different conditions, and analyzing and monitoring in real time a large number of switching parameters. This includes the rate of change, the di by dt in the gate current, in the gate, both in turn on and turn off, the peak of the gate currents, the charge, the gate charge, and so on. Most of these showed only very minor variation. Next, please. Most shows only a slight increase in the relative chip to input capacitance. However, the effect of this on the switching transient is relatively minor. With only a slight effect on a slowing down and the reduced oscillation frequencies in the gate to emitter voltages. This confirms that short-term effects of increased humidity penetration into power modules do not significantly affect the switching characteristics. But of course, this does not mean that the long-term effects are not significant. And this is introduced the next topic. Next, please, which is the more longer-term effects of humidity penetration on the reliability of power modules. One aspect that we are interested to understanding was whether the humidity creates more favorable environment for the occurrence of partial discharge. Partial discharge are high energy discharge events that can occur within voids in the insulation in the dielectric gel, and this can be caused by air bubbles or void due to imperfect curing of the gel. When these voids happens at triple junction, basically the conjunction point between dielectric gel IGBTs and the copper DCB or copper and ceramic substrate. This is where the partial discharge has the potential to create treeing into the dielectric gel and damage it, and longer term create an cumulative effects that longer term can lead to the failure of the insulation properties. To understand this phenomenon, we have constructed this test platform shown in the figure on the right, where we can create an high voltage DVDT up to 23 kilovolts per microsecond transient applied to the dielectric substrates on DCB rafts commonly used on standard 1.7 kV IGBTs for wind turbine. Next, please. We have conducted a very large number of experiments in different conditions, environmental conditions, combining various levels of temperature and humidity over the long term, over several weeks of testing. The first aspect is that the discharge event is a very high frequency into the hundreds of megahertz and into the gigahertz frequency range. So the signal processing to capture and measure partial discharge is quite challenging, especially in the presence of high commutation noise from the switching. So that's where we introduced the methodology shown in the top right, based on the processing of the moving standard deviation of the a signal captured by an high frequency antenna. There are a large number of tests and the results here, but in summary, we can conclude that the partial discharge events can be classified into two large categories shown into the middle column. In particular, we have identified the presence of strong, which means high energy signal partial discharge events, and weak PD events, which have much lower energy. And while the strong PD event do not show a significant dependency on the humidity penetration, the weak PD shows a significant change in frequency with the penetration of humidity. These results are summarized in the bottom right histogram, which you can see shows a significant increase in partial discharge events count when the modules are subject to a relative humidity environment of 85% humidity. Compared to the baseline of 30%. Next, please. So this brings us to the concluding modeling phenomenological explanation of these results, that shows that this identification of two groups of partial discharge events based on their amplitude, concluding that while strong partial discharge events hardly changed with humidity, these suggest us that these events happen more likely into the ceramic substrate, and therefore are not subject to significant ingress of moisture. Weak PD instead can be shown to vary significantly with humidity, and this can therefore be attributed to voids within the silicon gel, especially when they happen at the triple junction. A phenomenological model shown in the figure on the right has been proposed, which again shows a decrease in breakdown voltage, and therefore an increase in the partial discharge events and a decrease in the partial discharge inception voltage when the dielectric samples is subject to moisture ingress. Next, please. So this brings to the conclusion. So we have undertaken a number of investigations related to the reliability and influence of humidity on silicon gel performances as used in standard IGBT power modules. We have observed a significant increase in permittivity, which ultimately results in significant increase in equivalent capacitance of the silicon gel, which again is due to the ingress and penetration of humidity. orientation of power modules is likely to influence moisture absorption. Again, this can be an interesting outcome of this research and can influence the layout and construction of power converters in applications where this could be a concern. We have demonstrated that the short-term effects of humidity ingress on switching performance of power converters are probably not significant. Nevertheless, there are significant concerns on the long-term reliability in power modules when they are subject to this harsh environment. And in particular, we have demonstrated that that partial discharge is significantly affected by humidity. Therefore, this is a consideration that needs to be taken into account on long-term reliability investigation in power modules. Thank you for your attention. That's next slide, please. Just to summarize a couple of publications and presentation, other output of these investigations. Thank you.
Okay. Good afternoon, everyone. My name is Xiao Chen. I'm currently a senior lecturer in electrical machines at the University of Sheffield. So next, give you a brief presentation. Let's say to talk about a new project which is not kicked off yet. So I will focus on the background, the mindset, okay, and also the Gantt chart. And so first of all, the background of this project is so we'll see increasing number of the deployment of offshore wind capacity worldwide. And if you look at the UK offshore wind capacity, so we are expected to increase to 50 gigawatts capacity in 2030 from the 23 gigawatts now. And then in 2050, then this we expect it increase to 75 to 140 gigawatts. Okay, so this actually means there's an increasing share of power converter interfaced permanent magnet synchronous generators, which will replace the large conventional synchronous generators in the power system. And because these permanent magnet synchronous generators is one type of the popular topologies for the offshore wind turbines. And this actually means it will have increasingly more influence on the dynamics and the behavior of our power system. And to model those kind of dynamics and behaviors of power systems, and we need to have a high fidelity model of our permanent magnet synchronous generators used in the hardware in the loop testing. Okay. Next slide, please. So the main objective of this project is try to develop a parameterized permanent magnet synchronous generator model, which will be capable of running within the MATLAB Simulink first, and also in real time using the Oricatable's Opal IT simulator. And we are concerned with 3 stages in a life cycle of a turbine, including the pre-generated prototype. And this means we try to develop our model based on the design parameters only. Okay, and then the second stage is like the post-generator testing. This refers to, let's say, we will try to derive a model based on the test results and also the design parameter. And then the third stage is for the deployed turbines. Then in that case, we can only get access to the data from the SCADA, and then also the design parameter. We try to derive a model. And this particular project will initially focus on the first stage, so the pre-generated prototype stage. So which means we are trying to develop our model based on the design parameters only. Okay. Next slide, please. Okay. In terms of the permanent magnet synchronous generator model, and typically we have talking about 2 models. One is like a finite element model. So this type of model is have a very good accuracy, but let's say it's mainly for the machine design with, let's say, the current-driven sources. because if you use this one to directly do a simulation, then it will be very time consuming. And so when we talk about a simulation, then a more popular model actually is a voltage-driven simulation model. And typically we have this inductance-based machine model. And we also have another type is a flux linkage-based machine model. And in this flux linkage-based, is like we can avoid using inductance and we can avoid the assumptions in our inductance calculation. Because you know that for a permanent magnet machine, the d-axis inductance actually also contribute to the d-axis flux linkage, and the permanent magnet itself also contribute to the d-axis flux linkage. So it's because it's a nonlinear system. So the superposition principle no longer work. So it's difficult to separate them without doing the frozen probability. So usually when we try to work out the inductance, then we have some assumption there. And if we, let's say, avoid using inductance, just purely this flux linkage, then we can avoid this sense. And then another I'm talking about this flux linkage based model is we use this inverse flux linkage table, which is derived from the original flux linkage versus the current table. And in this reverse one, then it will become the current versus flux linkage. I will later on show you what this looks like. And then it can also avoid the deviation in the simulation. So it's good for the stability. Worth noting that in the machine model, so machine itself, will have the magnetic saturation effect. So which means the pH curve we used in the stator and rotor core itself, it have a nonlinear function there. And we will also have the spatial harmonics, which is typically introduced in the stator magnetomotive force. So when you excite a current in the stator winding, the armature reaction actually there, it will produce a spatial harmonics in the MF. And the iron loss itself is a type of energy or power. Of course, it will affect the voltage and current eventually. And the temperature effect is like when we have every 100 degree Celsius increase in the temperature, then our copper winding resistance, it will increase by like 39%. And the remanence of the permanent will also reduce. For the NdFeB material, then this remanence will reduce. For ferrite, it may increase. So it will be subject to the temperature as well. So in order to build a high fidelity model, we will also try to account for all these effects. Next slide, please. So this is one of the model we built before when I was a PhD. And so this is a model for the permanent magnet machine, and using the flux linkage based model and using the lookup tables of the current versus flux linkage. So which means it's a reverse relationship between the current and the flux linkage. And in this schematic, you can see in the core area or in the middle area, we have the voltage equation, torque equation, and mechanical equation. Those are the basic functions. And then on the top and bottom of this schematic, you can find some block which represents the temperature effect model and the iron loss effect model. And in the inside of the voltage equation block, you can see we have this ID with a function of psi d psi q theta. So that one, it means it's a d-axis flux current with respect to the d and q axis flux linkage, and also is a rotation angle theta. And so this one actually was derived from the IVA, and it can account for this the saturation effect and also account for the spatial harmonics, because we have this theta that represents the rotation angle. And based on that, we can have a high fidelity model, and it's also computationally efficient because the IVA is not involved in this simulation. So next slide, please. So a bit of summary of this type of model is we can have a good accuracy because we are based on the fundamental element analysis actually. And in the fundamental element analysis, we also calibrate the residual flux density as well, and also the temperature coefficient based on the measured in the nodal vacuum F. and also measure the temperature coefficients of the magnets. Then another other reasons, let's say, why this is relatively accurate is we already consider this magnetic saturation effect, because in the previous schematic you can see that we have the IDIQ function with the +D+Q, right? So actually it captures those saturation effect. Spectral harmonic is accounted by that theta angle there, and then the iron loss effect and temperature effect, we have some blocks which represent those two effects on the voltage and the current relationship. And it's also relatively computationally efficient because the finite element analysis itself is only involved when we try to derive the relationship between the flux linkage and the current. So once that is done, then the FEA, the finite element analysis, will no longer involved in the simulation. So for a 0.5 second simulation with 10 microsecond time step, then the computation time in this model is roughly 10 seconds for a PC, which is probably 10 years ago is like a core with a 3.1 gigahertz PC. Okay, next slide. Then recently, one of my PhD students, Wei-Qian Li, is also developed a neural network-based machine model. So the motivation for us to develop this model is the person model, although it captures also those effects, but when we try to solve that inverse relationship between the current and the flux linkage, actually it's quite a complex and tedious process. If we, let's say, can use this kind of machine learning technique, the neural network based algorithm to generate those, to model this kind of function, then it will be a better solution, we would say. And so in other words, we will treat those kind of relationship as a black box and then try to derive their relationship using the neural networks. And the data supplied to this neural network model would be the flux linkage and the current relationship, and of course also include the theta angle, rotation angle. For all these flux linkage and the iron loss, also this temperature effect block, all these three blocks, we can use neural network method to derive the model for that. And we found that the accuracy is similar to the lookout table based model we presented previously, and is also easier actually than the previous model to implement, because we do not do that inverse solution. And then it's more computationally efficient than the lookout table if the lookout table model use the cubic supply algorithm to do the interpolation. And on the bottom left, there's a table which is compares this simulation time, and we can see that those neural network model actually is in the similar level of this linear interpolation method for this lookup table model. And the time is much shorter than the cubic supply interpolation method. And it's also lightweight and more suitable for hardware deployment, because you can see in the table and the size of the model, the memory it need actually is much less, because we do not need to store a lot of lookup table data in this neural network based models. And for the iron loss itself, we compared and we found that iron loss is more accurate as well. And the data, the simulation time we compared in the table is based on a recent PC, is a 10 core 4.7 gigahertz CPU. Okay. Yeah, next slide, please. Okay, and here is the Gantt chart for this project. So it's a target on the six months actually. So we focus on task 1 and task 2. For the task 3, it will depends on, let's say, our programs, and then to see whether we can do more for this task 3. So task 1 and task 2 basically is for the stage 1. Basically is like we will derive a model just based on the design parameters. So it's for the pre-generated prototype. And task 1 is we plan to spend 3 months and to finish the high fidelity and computationally efficient model. and also the model validation using the product data. And the task 2 is try to implement it into the Opel RT simulator to do that hardware hardware in the loop testing. And this will be done by the Professor Antonio Grifo, so the previous presenter. Okay, and the task 3, the task 3 is a model based on the measured data, and we try to derive the flux linkage data from measured data instead of the finite element, and then try to develop the model and validate the model using the measured data. And this one probably takes 6 months, I think, count from the month 4 to the month end of month 9. Yeah. Okay. Yeah. Next slide. Yeah, because this is a new project which hasn't kicked off yet, so we don't have any conclusion yet. So here is just a reference. Yeah, that's the end of my presentation. Yeah. Thanks.
Hello, can you hear me?
Yeah, good, thanks. Yeah.
Okay, good. So my name is Nicolas Yusfidis, and I will be presenting my PhD topic, which is feasibility modeling and design of study for short-term overload capable modules for high voltage DC grid support. So my supervisors are Professor Liran, Dr. Denisenko, and Professor Philip Moby from the University of Warwick. And in line with my studies sponsored by the Catapult, I'm also in the CDT, the Center for Doctoral Training we have here at Warwick. Can you go to the next one? Yeah. So I will cover the application background and the motivation for the work, the scope of the work, and then 2 studies that we have done. One currently ongoing is the design of press spec thyristor modules that are based on phase change material cooling for static compensator short circuit protection. And the other one is for design of short-term over capable modules for IGBT power module for grid support. Then I will be talking about some of our conclusions thus far and some work that is currently being done. Next, please. So in any grid that has voltage source converter is becoming the backbone technology. So it keeps increasing in grids that have large penetration of wind or other renewables. It is flexible. It gives flexible operation. It has 4-quadrant operation. And it also is required to have a grid fault right-through capability, meaning that according to the UK grid standards, they need to maintain grid connections so the power energy generation is immediately available after the fault clearance. So the key to finding out this, the grid fault capability is to establish an appropriate level of transient overcurrent capability. Can you go to the next slide, please? Next one, please. Yeah, is the so the overcurrent capability is limited by the overheating of the semiconductor chips, be it in a thyristor, which is a disk, or in IGBT and diodes, or maybe later in MOSFETs, silicon carbide. So for silicon-based modules, the maximum operating temperature of silicon is 175, and the steady state should be much lower than that. So we have durations of the grid fault events that can happen from tens to hundreds of milliseconds all the way to, let's say, 30 seconds. And the multi-layer structures of power modules that you can see, a couple of them, the conventional press pack thyristor module and the IGBT power module, they have so many layers, a few layers, 7 for the IGBT, that have materials of different thicknesses and of different thermal conductivities. So there is an inherent thermal impedance between the heated junction and the heatsink. So for very small transients, like let's say 200 milliseconds, and then the external heatsink, just because of this time delay between the heatsink and the heated junction, the external heatsink cannot respond quickly to the temperature rise. Moreover, in longer transients, maybe the cooling capability of external heatsink is not sufficient enough, because when we build a system, we don't assume, we test it with specific conditions with heatsinks included. However, if we want to increase the current rating, maybe this cooling arrangement is not sufficiently good enough. Can you go to the next slide, please? So the scope of work is technically a feasibility study of over-capable modules to enable grid support. We have simulated perspex thyristors for very high current transients up to 200 milliseconds, and the cooling solution was phase change material cooling, which uses the latent heat of fusion of the phase change material when it changes from the solid to the liquid state. And for the wind turbine modules, we have tested already for transients up to 30 seconds for 1.5 per unit current, or continuous for slightly lower current. And the solution is microchannel water cooling, and the cooling mechanism is convective heat transfer, like in one regular heat sink, or sometimes the latent heat of evaporation of water when the heat flux is very high, when chips are required to inject a way higher current than they're supposed to. Next slide, please. So when you have a series static compensator, and then you have a fault along the grid lines, then because these compensators normally work with IGBT modules and they cannot handle very, very exceedingly high currents, one way to protect them is to divert the current into thyristor modules. We're using thyristor crowbar circuits. Meaning and you have to, so these thyristors have to conduct the current until the circuit breakers are triggered, and then the static compensator is isolated. So for this study, if you go to the next slide, please, we have integrated in a spiral, co-sending spirals, the phase change material that has 50 degrees C melting point and has a latent heat of fusion of 45 kilojoules per kilogram. And we will be testing according to some commercial device, according to some commercial thyristor modules for 2 ratings. We have taken, if you go to the next slide, please, we have simulated the thermal response over 200 milliseconds for one conventional thyristor package and one with this integrated. So as we can see on the left graph, technically what I told you earlier, because the overload event is very quick, is 100 milliseconds. So any type of external cooling solution you have is not fast enough, so it cannot mitigate the heat quickly. So what you can do is integrate something in the existing structure. Now thyristors have anode and cathode, which is copper blocks. So by integrating this bismuth alloy phase change material, you can have simultaneous conduction of current, because this is a liquid metal, and also you can have phase change cooling. And now if you see the graphs on the right, on the middle, on the right, we can see a 13 degrees C reduction using this PCM at 30 kilo ohm current, and the 10 degree in the 4.2 kilovolt thyristor. For the middle one, it actually takes it from the maximum rating to slightly less than the current, which in silicon devices it will probably it would avoid any instantaneous faults. Go to the next slide, please. So this is the bulk of the work that we have done here, and in my PhD for experimental based. So it's a feasibility study of microchannel cooling during overloads for up to 30 seconds. So the aim is simple. It's just contain the semiconductor chips temperatures within the safe operating limits. By design, this microchannel array will work as a supplementary cooling solution and not as the only one, but it's supposed to be there to give a faster cooling response to the temperature rise during the overload event. Next slide, please. So the proof of concept will be demonstrated in a 650 volt, 300 amps silicon IGBT diode module. So some thermal simulations introduce the problem. So as you can see, before the overload, we have a delta T between the diode, the heated junction, and the base plate, the top surface of the base plate of 25 degrees C. And during the overload, this becomes twice as much. That is because of the thermal mass between these two materials And because we have two layers of solder there, we have a lot of the highest thermal resistance in the structure itself. So if we could integrate any sort of cooling arrangement there between the heated junction and the top side of the base plate, we will have faster cooling response while maintaining the electrical insulation. And the losses that are used for the simulation were based on an Infineon module quoted there, and the heat sources are used for, diodes are used as heat sources, resembling a DC cycling test. This DC cycling test will be used a bit later in the experimental validation. Next slide, please. So this is the design that we are proposing. On the left-hand side, you can see the CAD design and the CNC machine design. It consists of 38 channels that are 400 by 800 microns cross-sectional area with 600 micron spacing in the walls. We have used CNC machining to realize it here at Warwick. And they have common inlet and outlet plenum, and they are just shorter on the lateral side to ensure similar hydrodynamic resistance. So technically, we need to have this in order for the water to flow uniformly in all the channels, which can be seen in the CFD simulation in the middle. Is 1 minute for me? I'm already 10 minutes.
Yes, thank you. Yeah.
Well, I still have a lot of slides. And can you go to the next one, please? So in order to verify these concepts, we have done two tests. One is the visual inspection of the flow under the temporary device overload. So in this design, we have soldered the microchannels on the bottom side of the base plate in order to see what's happening to the channel domain during this overload event. We are observing it with a visual camera, and then we're monitoring the diode temperature. So the feasibility criteria is to avoid any sort of instability, such as the boiling crisis, where all the water is vaporizing, or any other sort of instabilities like pressure oscillation. Next slide. So here is a temperature response during this 1.5 per unit current overload. You can see that on a base plate only, that 0 milliliter per minute is a base plate only, like would be in a conventional structure. The temperature is 160 degrees C. However, it reduces all the way to 100 degrees C by using water flow at 100 milliliter per minute. Next. So this is from a visual inspection at lower flow rates, we are observing evaporation of water, and we need to quantify things in order to be sure that we will not have any instabilities there. So before the overload, we have single phase flow. During the overload, we have some evaporation, which we analyze with image analysis. And in the worst case scenario of this, we had 65% of water and 35% of vapor. Which happened, also the vapor is located literally below the chips. But there was no sign of boiling crisis, and there was no sign of different slope in the temperature rise. Next one. So we then used the Siemens power tester to quantify this in terms of device characteristics. So we swiped over the range of flow rates to see how much is the thermal resistance reducing by using microchannels. Next one, please. So from, bear in mind that this one has only one diode, and the RTH was 0.4 for the conventional design, whereas it reduced by 20% for the diode at 100 milliliter per minute, and it is around, it's more than 25% for the IGBT, but I don't have it here. And next slide, please. So the summary of the results is, by using microchannels in this design, we can reduce the RTH for the diode by 20%. And this is demonstrated by a visual inspection of the DC cycling test to ensure that we don't have any instabilities there. And we can see that the temperature plateaus at 100 degrees C during this overload test during DC cycling. Next slide. So some conclusions is, for press pack thyristors, we can, since they're used only in reserve, we propose a passive cooling solution with phase change material cooling, which is also an electrical conductor. And for microchannel cooling, We have reduced the junction to case thermal resistance by 20%, which can be used to increase the nominal current operation by 20% in steady state. Or it gives you a bigger headroom if you want to inject more current, and you can reduce the maximum temperature below the maximum limit. And the next slide is the ongoing work. So I will be testing these devices under switching in a back-to-back test rig. And then we will be evaluating the two-phase flow condition, under which conditions we can use two-phase flow. But the key challenges are, again, the flow boiling instabilities. Any alternative designs may be tested until the remaining, until I have to submit my thesis. And that was all for me. Thank you. Thank you very much.
Hi everyone, I'm Yang Hao. I'm the PhD student of the engineering at the Warwick University. My academic supervisor are Professor Suraj and Professor Lee. Lex, please. Lex. And today I will briefly introduce my project to you. Now the content list show all of my pre today. First, I will introduce some of my work motivation, and I will show the test rig and the algorithm framework. And I will present what I have done, some results from the simulation data. And at the end, there will be some conclusion on the outgoing work. Next, please. Wind energy is one of the most popular directions to solve the renewable problem. Some new type of semiconductor device like the wide band gap has begun to be widely used in this system, and the converter of the offshore wind turbine in particular worth of attention, because the working environment of it is so special and is far from the land, and the complex weather at the sea doesn't support the high frequency contact with the meteorology. And the research results show that the failure rate of the power converter in wind turbine system is so high, and the downtime is very long, and the converter is not only critical component of the powertrain, it's also critical component of the cost, power loss, and the system failure. Most of the semiconductor power device failure, whether on-chip or the package related, are thermal triggered. Next, please. IGBT model in wind turbine converter face a high thermal stress and repeated thermal shock and causing wear and the failure. But the silicon chip or silicon combined chip didn't age quickly, and the bond wire critical and the soldier layer wear are main causes IGBT failure. To describe the degradation of the device over the time and the percentage change in the thermal resistance of the module is often used. The most direct impact of changes in its is the junction temperature of the chip. Therefore, it's important to monitor the condition of it. Next, please. In the real SCADA data system, we face the problem is the thermal resistance of the power module cannot directly measure, and the aging process of the module is slow, and the thermal resistance rests slowly. The purpose of the experiment of mine is to monitor radio aging of the IGBT module in the offshore wind turbine converter from the SCADA data by using the machine learning module. In the past, machine learning was rarely used in the field due to the data difficulties and the weak linear algorithm. Classical physical modeling was preferred. Recently, Ireland type linear network, which are the better for the time series data, has been used. In my project, I would prefer use a new module like the transformer or the attention LSTM, because both of them include attention measurements. The simulation result of my show that it improves prediction. Next, please. In my experiment, I using the test bench with two microhenry inductive loads, and the system output voltage to 200 volt and the current amplitude to 440 amps. We are using the Infinose 1.7 kilowatts, 1 kiloamps IGBT half bridge module with a 6 chip in parallel. One side of my test bench emulates the wind turbine, and the other side emulates the generator side converter, and the rest side using the current control to make sure its output current is same as the wind turbine side. Next, please. To design the module with a different thermal resistance state, we created the addition Cooper base plate. The thermal resistance can be adjusted by changing the thermal interface material under the chip. And the Cooper plate matches the size of the IGBT base plate and has a groove the beneath the chip. These grooves hold the different thermal conductive material, so just the vertical thermal resistance. The range is from 5% to 20%, because the director judgment standard for defining soldier failure is based on the steady stable resistance increment 20%. Additional, our through channel below the groove allows for the placement of the fiber optic temperature sensor to monitor the base plate temperature. Next, please. The process of the thermal resistance prediction model is shown in the graph, and the data come from the 1 Hz current data of the real offshore wind turbine supported by the couple. And the current data is processed through the control calculation and the RT box to the output to the SPW control signal, and then a real temperature and the electrical data collected from the test bench, and the thermal resistance information is from the console thermal the physical thermal simulation. Finally, all the data is fed into the machine learning for a prediction model. Next, please. Compared to the DNN or some simple linear network, the largest structural difference of the LSTM is their ability to learn iteratively. By using logical gates like the as an input for gate or output gates, the LSTM can selectively keep or discard the filter during the training, and leveraging long-term dependence. LSTM can keep can return the information, but accuracy will be decreased with a longer prediction. The attention matching dynamically weights the junction temperature feature to adjust the focus during the modeling. It weights to the relevant data, helps the LSTM achieving a long-term multi-stable prediction and reduce the data filter loss. And the LSTM combines the autoencoder fault detection system with attention matching, include the training, testing, and the fault criteria. Both the training and the testing set has aging data and with healthy data showed by LSTM autoencoder, and the fault threshold is defined here. After the training, module parameter predicts the test set to determine the thermal resistance increase, which started raising in 4 months. This setting is for my simulation dataset. Next, please. Before I using the test bench data to verify the use of the attention LSTM, a steady state electro-thermal simulation was built using the MATLAB Simulink. And this simulation data presents the relationship between the current and the wind speed and the junction temperature and the thermal resistance here. 4 different thermal resistance increase rates were set and observed the advantage of the LSTM in long-term agent behavior. The total simulation time length is about 1 year, and the wind speed level is limited to the median wind speed. Next, please. here are the result. There is a result for my thermal electrical simulation data results. Here are the 4 prediction results displayed here, showing the prediction of the junction temperature by both the DNN and the LSTM single step. And the single step LSTM is like the DNN and can report the 99% of the data information within 2 minutes for prediction of the healthy data. But the LSTM structure has a higher linear accuracy in the prediction data with the slow growth of the thermal resistance in the non-healthy group. And it means the LSTM is a more generalizable than the DNN in the term of the time continuous data. Next, please. And this table shows how the attention matching improves the multi-stable prediction of the LSTM, and the attention matching has improved this problem very well. As the step size increases, the R2 score of the 80 attention-based LSTM can decrease at the lower rate than the LSTM, even if the data of the next Friday, next Friday is predict. R2 score is the similarity score can reach 90%, but attention LSTM also has a longer training time due to the complex calculation. Next, please. Therefore, four picture results showing the comparison between the restriction error of the autoencoder and the threshold. The red line means the threshold for the healthy state. It can be seen from the comparison of the results for the stabilized grazing on both LSTM and the DN can detect the data drift at the place where the thermal resistance increased by 20%. But if the thermal resistance rests slowly on the 3.3% per month, and the LSTM can also give the earlier warming 2 months before the module is completely aging. Next, please. In conclusion, LSTM's linear network can capture and use the long-term patterns in the time series data, especially with clear trends or circles. LSTM can predict the multi-future points at the once, helping with the real-time decision and the long-term plan, when making the online process more efficient. LSTMs with the autoencoder are better at the supporting long-term changes in data than DNN. The attention matching can help LSTM focus on the important information and improve the accuracy in non-sequence prediction. Oh, that's all. Thank you.
Great, thank you very much. Thank you very much to all of you who've stayed until the end. I want to say a big thank you to the speakers today and all of you for attending. We're already over, so I guess we can wait for a minute or two. If anyone has any questions, just put them in the Q&A panel. If nothing, thank you very much for your time, and let us know if you have any questions. Take the lack of questions as a time to leave. Thank you very much, everyone. See you next time.
Thank you, Dai.
Thank you. Thank you.
Thank you, Dai.
Thank you.
Thanks.
Thank you.
Thank you, Dai. Thank you.
Thank you.
Right.